So moving on. So let's talk about sp hybridization. I want you to recognize sp hybridization is synonymous with the geometry linear. Okay? And what happens in sp hybridization, only one s orbital mixes with one p orbital. And then so what we're left with is two p orbitals. Or two electrons, two unhybridized p orbitals. And this is what will form a triple bond, which a triple bond we recognize is 1 sigma and 2 pi bonds. But this is where this gets a little tricky, okay? So what I have here, let's try to draw this, okay? Or not draw this rather, but let's make this molecule, okay? So the first thing I'm just going to show you are only my sigma bonds. And so by the way, this molecule that I have right here, carbon triple bond with 2 hydrogens, this is what we call acetylene. And yes, that's the same acetylene. If any of you are machinists, or maybe you know people who are machinists, acetylene torch is what's often used in welding. So acetylene is quite flammable. So here would be my sigma bonds, right? All of the single bonds, okay? And now because there are 2 p orbitals, we have to remember that these are going to be like px, py, pz. So these 2 things sticking up right here make one of the p orbitals, which, you know, combining this toothpick and this toothpick makes the pi bond. However, and this gets really hard to see because my Play-Doh just doesn't want to hold up, that other pi bond is created at a 90-degree angle, right? You see that? So really, I've got now 2 off-axis bonds. I've got the internuclear sigma bond, which I'm pointing with my ring finger right there. I've got this pi bond that's on top, but now if I rotate it 90 degrees, right, that's what's going to make my 2 pi bonds. So really, I kind of like to describe this as a barrel. It's like a barrel of electron density surrounding the internuclear zone. And so hopefully this picture makes good sense, right? Here is a sigma bond from carbon to hydrogen. Here's a sigma bond from carbon to hydrogen. Here's another sigma bond from carbon to carbon. And now I'll have 1 pi bond that's above and 1 pi bond that's 90 degrees relative to the other one, okay? So there's a ton of electron density surrounding this carbon-carbon bond, all right? And that's why the bond is so short and strong. Remember, we talked about that in chapter 8, that triple bonds are very short and quite strong because there's all of this electron density surrounding those carbon-carbon nuclei, okay? So moving forward, so we can get pretty complicated with this, even for simple molecules like CO2, all right? So with carbon dioxide, okay, this may be hard to recognize, but what I want you to see is each carbon, or the carbon, takes on an sp hybridization because it's linear. But if you look at each oxygen now, there's the double bond, that counts as one thing, you know, in my steric number, and 2 electron pairs. And so that means each of these oxygens are sp2, okay? And so I'm not even going to attempt to make this with my Play-Doh because I think it'll fall apart. But if you look at this model now, okay, what I have here is my carbon, my central carbon atom. The yellow represents the sigma bond, and I'll put electron pairs in there. So that represents the internuclear single bond, right? The bond that exists between the 2 nuclei. But now, and hopefully you can see this in this computer drawing. Because carbon is sp hybridized, it's got 2 open p orbitals. Remember, this lobe, the top and bottom, counts as 1 p orbital, and the lobe to the left and right count as 1 p orbital. And so now one of these double bonds gets created up here above this sigma bond. And then the other pi bond gets created out here, like coming out towards you. So it's kind of twisted, right? The electron geometry is twisted about the carbon atom, and that helps these electrons avoid each other as much as possible, right? The electrons want to spread around as much as they can. So CO2 is not like, you know, two double bonds on the same plane. It's one double bond above and one double bond out in front of you, 90 degrees, like that. Okay, hopefully you can picture it.